talk about the conditional distribution, then we are referring to the function, the marginal function of x. So conditional distribution of x given y, it is by definition this fraction here. It is the joint distribution divided by the marginal distribution for y. And if for each value of y in the range of y, the function this is indeed a probability function, so we are saying that this conditional distribution is also a probability function. What do we mean by it being a probability function? It should satisfy the conditions here. One of the conditions is that if it is a probability function, then it should be non-negative for all values of x and y. If it is a probability function, then when you take this sum, you should get 1. Now, taking this sum over all x is the same as taking the sum over all y, all x, of this, and when we sum this one over all x, we get the f of y, which is also that, and then we get 1. So it means it is a probability function, and the conditional distribution of y given x, it is given by y given x, then it is this fraction. This is conditional distribution of x given y. This is the one for y given x. So there is this example. It's what took me back. So we have a joint frequency function of x and y is given by the table below. This is the discrete, because we have y taking on values 1, 2, 3, 4, and x is also taking on values 1, 2, 3, 4. So we said when we sum over this column, this is f, this is the marginal probability function of y given y equal to 1. So when y equal to 1, when we sum the column, we get that. Then when we sum over the row, this is the marginal distribution of x given x equal to 1, x of 1, marginal for x of 2, x of 3, and so on and so forth. So we want to find the expectation of the conditional distribution of x given y for that. So, and to work out this, we are going to get expectation of y. For y, we'll be looking at these values here. These ones, these are the totals. So we know that the conditional distribution of y given y, we have to use this formula now. We use this formula to get, we get the joint distribution, then we divide by that of x to get the distribution of y. So we first get the distribution of y, then after that we get its conditional distribution. I want to share the solution now. Let's see if I can get the solution. Yeah, it's this here. Yeah, let me get, yeah, it should be this. So this is what we do, the expectation, from the definition of expectation of y given x is x, it is the sum over all y, then y times this. But we know from formula to get this marginal, then we get the joint distribution, we divide by the marginal for x. So we first find expectation of y given x equal to 1. So it means we sum over values of y. So when y is 1, we get 1 times times, this is the margin of 0.1, 0.10, then 2 times 0.05, this times. So we add over all those values of y, then the marginal, this is the marginal for fx equal to 1, for x equal to 1. So we divide by 0.19. So we take the sum. So it's like we sum over the joint distribution for y, and then we divide by 0.9 because 0.9 is the fx of 1. So that one gives us this value. We keep it. Next, we work out the one for x equal to 2. So it is 1 times 0.05. Then we divide by the one for x equal to 2. We get to this. Then we similarly work out the one for x equal to 3 and x equal to 4. We divide, and then the expectation of x is equal to x is this sum. So we add all the ones we got, and that one gives us this value here. We get this value as the value for the expectation of this sum. So we just sum over the values of y equal to 1, y equals to 2, y equal to 3, y equal to 4, for x equal to 1. So after summing them, then we divide by the joint distribution x equal to 1, x equal to 4, and so on and so forth, and so on and so forth. So that's how we get the conditional expectation. I hope we are together, members. Are we together?
Yes, sir.
And so let me go back to the slides we are sharing. Talked about this. Next, we want to talk about the variance of sums. Want to talk about the variance of sums. Katongo is having issues with its network. Okay, variance of sums. And we start by a simple definition. We record the other property of expectation, which says that expectation is a linear parameter. Expectation of the sum is the sum of the expectations. So regardless of the joint distribution of x and y. So the same is not true for variances. For variances, we can't have this regardless of the distributions x and y. So the following theorem simplifies calculation of variance in certain cases. So we look at the theory. It says if you have two random variables x and y, and u is a linear combination of the two random variables x and y plus a constant c, then the variance of u is the same as the variance of this sum, of course. And the theorem tells us that this is equal to a squared variance of x plus b squared variance of y. For expectation, we expect to add a constant, but for variance, we add 2 times ab, then covariance of x and y. And we are going to prove this theorem. So this is the theorem that helps us to compute the variance of sums. This theorem helps us to compute the variance of sums. So if x and y are independent, then we said for independent random variables, this covariance, the covariance is 0. If they are independent, then the covariance is equal to 0. The covariance is equal to 0 if they are independent. So if they are independent, then we have a squared variance by x plus b squared by y. Okay, we want to prove that simple theorem. we start with the expectation of x being mu1. Expectation of y is mu2 because this is the mean. So we can let this be constants, mu1, mu2. So expectation of this sum is going to be a expectation of x plus this plus c. From properties of expectation, we have this. So it means that we get a, this is mu1 plus b mu2 plus c. So the variance is the same as this expectation minus this squared. This is the formula for getting the variance from the expectation. So this is going to be, we can now put like terms together. So we get a into x minus mu1 plus b into y minus mu2, then we square. So when we expand, when we square inside, we get x squared, b squared, plus b squared, y squared, plus 2ab from the other identity for expansion, a plus b squared. So 2ab into this and that. So this means that we get, when we take the expectation inside, because a is a constant, so we get x a squared expectation of x minus y squared plus b that plus 2, then the expectation here, and this is equal to a squared variance of x. This is again the formula for getting expectation. I mean, this is the variance. So this is variance of x. This one gives us variance of y. And this is the formula for the covariance. So that one, so this ends the proof for this theorem. It ends the proof for the theorem. Next, we look at a simple example. In this example, we have two random variables, x and y. Variance of x is 2. Variance of y is 4, and the covariance is negative 2. We want to find the variance of this random variable z, which is a linear combination of x and y. So from what we saw, the variance of z, which is z squared sigma, is this for the sum. Then the formula says this is the a squared, so a is 3, so 9 variance x plus 16, because this is b squared. B is negative 4, so negative 4 squared, we get 16. Then this should be plus 2ab. A is 3, B is negative 4, and then we get 24. That's why we have the negative, because the other one is plus. Now, next is the simplest substitution. So z is going to be y is 2 plus c. The other one is 4 minus c. This is 24. So we get the variance as 130. We get the variance as 130. Okay, next we look at another example. We have x and y. They are random variables. X and y are random variables. And they are independent random variables. Variance of x is equal to variance of y until 3. Find the variance of x minus y and variance of 2x minus 3y plus 1. So since they are independent, the variance of x minus y, remember, variance of the sum says we get a squared var x plus b squared var y plus 2ab cov xy. So the covariance is going to be 0, and the a is 1, so 1 squared is 1 here, minus 1 squared is also 1, so we simply get this, and so we simply add to get 3. The variance of 2x minus 3y plus 1, 2x minus 3y plus 1, from the formula, it is 2 squared, which is 4 then per x, plus negative 3 squared, which is 9 per y. since they are independent, the covariance will be 0. So this will give us, we substitute in this formula, 4 times 3 plus this, we get 39. Another example, we have x and y, they are random variables such that variance of x is equal to 9, variance of y is equal to 4, and the correlation, this row is the correlation is 1/6, where row is the correlation between x and y. Determine the variance of this sum. So for us to define the variance of the sum, since we are not told about the independence of these ones, then we assume they are general. So we need to use the covariance. So we know that the covariance gives us the correlation. Correlation is the ratio of covariance divided by the product of the standard deviation. Remember, these ones here are all is standard deviation, not variances. Variance is sigma squared. So you take the root. If you want, you can keep the root and then write sigma squared. Or you can just write sigma x, sigma y. You find the standard deviation of x and the standard deviation of y, whereby the standard deviation is just the square root of variance. So the variance is squared. So when you take the square root, you get the standard deviation. So we are given this correlation as -1/6. So that means the covariance of x and y is equal to that. But so that means covariance is -1/6 times z. When we cross multiply, we are here. Now the variance of x is 9. That means the standard deviation of x is to variance, which is 3. The variance of y is 4. That means this one, sigma y, is going to be 2. So when we multiply, we get -1 as correlation. Now variance of the sum from the formula here, we have 1. So this is 1 squared plus x plus 9 plus y plus 2ab. So a is 1, b is -3. So we get -3 covariance. But the curve here we found -1. So when you put it here, we get the answer as negative.
Excuse me, sir.
Yes, please.
You're saying the formula is a squared variance of x plus b squared var of y.
Yes.
Plus 2ab
A.
covariance.
Yes.
But now, why do you have a -3 instead of a -6?
The reason why I have, no, it's not a -6. When you look at this term, are you seeing where my cursor is? Are you seeing where my cursor is?
Yes.
Yeah, so when you look at this term, the A is the coefficient of x here, which is 1. B is the coefficient of y, which is -3. So this is supposed to be plus 2ab. It is supposed to be plus 2ab. So it is 2 times 1 times 3. Okay, yeah, I get your point. This is supposed to be -6. This is an error. Okay. It is true, this is supposed to be -6. So let's put -6 here and then we get the right answer. Are we together now? Hello?